Okay, so welcome back to the second lecture. This time it's about unsupervised clustering and some of the applications. And it's a little bit out of the scheme in a sense that normally I would continue now and would say machine learning isn't that easy. We need some part of the theory, which is statistical learning theory, at least a little part of it, and theory of generalization. However, in order to have a more practical applied session here, we go a little bit now into the unsupervised clustering world of doing some practical exampling using a parallel clustering algorithm, and then we go back towards the end of the day of going more into the theory again about learning from data and so forth. And we'll be a bit integrated because we're doing now practicals. That means we stop here and there if you see there are too many hands up in terms of having problems with submission to the cluster. We have here a couple of distinguished experts sitting that know the cluster very well, and that will help you. That means if we do some practicals and you have no idea how to proceed, or basically I cannot go in all of you in detail, right? Because we're a big class. Raise your hand and one of these experts will actually come to you and help you here and there. However, if I see there will be too many hands raising, I of course go one step back and then we go to the practicals. However, before we start with clustering, I need to bring across a little bit more about clustering, what it is about, and what applications it has. And it's a little bit under-expected perhaps, because you think like clustering is unsupervised and it might be not so interesting applications, but we have a couple of them in the point cloud domain which are quite interesting. However, just for a short review what we did in lecture 1, so that you don't forget this material, let us just, let's say, summarize what was the most important aspects of it, okay? So the first one was when you have a practical problem, we said like always check the 3 parts. If one of these is not really satisfying, it doesn't make sense to do machine learning, right? If there's a practical mathematical formula, perhaps it's much better to just implement the formula in the source code and use it, right? Instead of approximating some mathematical formula, as you have learned what we basically do in machine learning. And of course, the data aspect is a very important one. And someone was in my break and was asking about the data quality, right? So this is, of course, a very important point. Not only data exists, it should be in a certain quality. If there are almost everything with missing values, if it is very, let's say, a dirty data set, then you maybe don't use it at all. So data exists, maybe also including checking a little bit on the data quality, what's really there, and can you really use it for learning? Right? It also reflects to the amount of data that needs to exist. That is something what will materialize in lecture 3. We need certain samples actually to get some learning going. Then the, just realized I should probably use my microphone. Sorry for the back row. Oh, we can hear you now better. Okay. So these were basically the key ingredients you should check. We learned basically about the simplest learning model that you can have, the perceptual learning model. What it does was basically a linear decision boundary. We will see basically tomorrow that linear decision boundaries are very simple, and we have much more interesting decision surfaces really we talk about in practice with support vector machines. We had linear with separable data with the iris dataset, a very simplistic dataset, just to bring you know basically the idea of machine learning across. If you go to practice, linear separability is almost never really the case. And also the perceptual learning algorithm is something you heard now in the first lecture, but when we come to support vector machines tomorrow, you probably will drop that in your memory and will stick with support vector machines. And those of you who are attending also deep learning, I heard there's a kind of overlap with the audience. There will be much more sophisticated models. However, we learned that in a sense, a perceptual model is a key building block still of neural networks and deep learning algorithms. Then at the end, towards the end of the first lecture, we learned a little bit these different learning approaches, and we focused a little bit on supervised learning in lecture 1. If you remember, we had always X and a Y as an output that is guiding our learning. So what we will focus in this lecture is the second part, unsupervised learning. So what can we do if we don't have labels, if we don't know here the colors, for instance, in this schematic or in this figure? So as I was saying earlier, this situation is not totally hopeless, only because we don't have any labels. So it's the second part of the lecture series, which actually consists of 3 parts. The first one is really getting you involved a little bit more into the unsupervised world in terms of clustering. There are other unsupervised learning examples. You can do deep learning in an unsupervised way. But here we focus really on clustering, in particular to actually look how DESCAN work, because we will later use it in parallel on the clusters that are here. In order to have a good data set that we will work on, we will look on some application domain, which is a point clouds. It is a very interesting domain about laser scans, and we have also some interesting videos, very short, just to show you the power really of those laser scans and the point clouds, where you will be amazed. And then a little bit more technically, and the third part would be now your hands-on part, right? That includes everything, like we will discuss how you not only log in, but how you create job scripts, how you basically check the outcome of the job, and all of this. And if there are problems, don't worry about that. So we expect that in a way, just raise your hands, and then the experts will basically help you, and I will stop here and there. However, everybody of you should have an account. I don't know if a few people are new, didn't have lecture 1. So if you don't have an account, please talk, for instance, to one of the experts now, right? If you don't have an account, the one that was just coming right next to you is someone who can help you, right? So this is, of course, very important that you can log into the machine. That is what we assume right now. So let's go into some more interesting material about machine learning, clustering as the kind of second big group in machine learning, and there are lots of clustering algorithms. I just focus here on a couple of them. If you remember, it was really like using some kind of properties in the data, like here the Euclidean distance, also sometimes called the ruler distance, right? To find out maybe there are different groups, and there could be different group properties. It must not be the Euclidean distance. But this is the one that we mostly refer to here in the tutorial. So we have the second part, which is, you know, as I said earlier, also often applied before other learning takes place. Right now, if you think about that you basically have a large point cloud, somewhere laser scans, and you cluster them, you maybe together get a building. With a building, you then can build classes. Is it a church? Is it a normal residential building? Is it, I don't know, maybe even a tram, not really a building. So you can use that before classification to create classes, so to speak. It's a nice property of this unsupervised learning, which means we want to uncover something which is in the data, which is not explicitly known, but there is something to it, some process that we will basically look about. So if you remember, mathematically that means for us, we don't have any y, not any given output we can follow. And this makes it a little bit more different for the machine learning algorithms. So hence, this learning process of saying typically how you would learn for an exam, with, you know, a test exam, for example. You would go through a test exam, take your tasks, and you have already for the test exam the correct output, or for the assignments the correct output, and you learn from that and would improve yourself. So how we improve if you don't have any guiding output? So these are all the challenges for learning algorithm we have to look at, because otherwise we don't learn at all. Hence, the algorithms are sometimes a little bit different than those that are supervised, and we will learn about that during the course of this lecture. So, and there are different data sets where you can use this kind of clustering or unsupervised learning, and I just brought here 3 where we are personally involved, and you find they're out in practice, or if you go to the UCI machine learning repository from lecture 1, much more example. So one of them where we basically have you a little bit already known about this is Pangaea, data collection, where we, out of this, we have some specific time series where one of my PhDs is basically analyzing water mixing events. So it's somewhere deep in Sweden, there's this kind of fjords, which mixing then ocean water with, you know, inland water, and the salinity and temperature and so on is measured. So you have a nice time series, and what you really look at and would like to find is basically water mixing events, because it has huge impacts on the vegetation basically in all of the fjord. So this is something what the people and the kind of scientists together with the PhD students have achieved by using clustering in the time series across different, you know, temperature, salinity and other measurement things. You could have identified water mixing events. No one was telling you that this water mixing takes place there, but you can actually identify it by clustering time measurement data. So quite interesting, and then of course you talk to the domain scientists, they're starting now looking at this, they have a huge time series to look at, but if you give them just those where the mixing takes place and they check that and see, oh wow, that's really interesting, it is indeed a water mixing event, right? Specialists know that. They can mark it as labeled, and from that we learn even better. So this is a typical process in that. In the human brain, we had already the example like clustering of cells, right? We have the brain slices. So no one tells you that there are specific regions in the brain. Rather, you have here the cells with a particular, let's say, distance to each other. And when you run our clustering algorithm that you see here, it builds different clusters based on the density. Zoomed in, that doesn't tell you anything, but zoomed out, you have seen the colored scheme of the brain automatically done. Right? No one was telling you supervised anything. It was unsupervised learning of this cortical layers. Now, what we will basically focus on will be the point cloud data. So I'll leave that out for a while because we have, let's say, a couple more slides around that. So this is an interesting aspect where I said time measurement data in the Swedish fjord based on real measurements. And of course, this relates to some aspects we already discussed also in the brain, data quality, right? So an interesting aspect that you should consider when doing machine learning is, for instance, here this example, that's why I brought it up, that these buoys that are swimming partly here in the fjord to get you measurements of salinity, of temperature, they actually were degrading in terms of measurements over time. So they were kind of noise data, very much, the signal was getting, worse over time. And what was the reason? Biofouling. So actually there are little creatures living now on the buoy in the ocean, and as the thing moves and over time it's just in the ocean, it's getting bigger and bigger. What I mean with this is, this could harm the learning, right? When you have basically a pattern that is in the data and suddenly the data quality is changing, of course this is changing significantly your model as well, right? And this is an effect we call rubbish in, rubbish out in machine learning. When you have stupid data in, you get stupid data out, right? And this is something to consider wherever you go when you do real measurements of data in the field. Could be not only in the ocean, could be some other degrading measurements from some engineering kind of measurement device. This is something to consider. Quality of data is an important aspect, especially when you think about you want to uncover unsupervised. Right? If you have supervised, then you quickly come to the problem probably that there is somehow here a strange thing in this kind of measurement. Right? It's much more easy to detect this error. When you do unsupervised things and aspects, this is crucial because then you think, no one tells you anything about the data set, you do it, and you learn basically the noise of this biofouling with the data set. Just an example of that. Then the other example I want to show was again this human brain data set, because here you have a big trouble, it's just too big. Right? So when you now use MATLAB, R, you will fail. Right, DESCAN, for instance, on this serial implementation has no chance. Here we're looking at multiple gigabytes of an image. So here's something where cells of order of magnitudes are counted in order to get clusters. So that just as a stimulation that we are at the forefront, just beginning of using parallel programming and parallel computing and supercomputers, clusters for the data analysis. When I now think about the whole brain, so this is just one slice, when we stack that up, we get to terabytes of data, basically, because what you want to see also is, of course, this as a 3D reconstruction, right? The brain is not a single slice, it's a 3D reconstruction. And we have, let's say, a couple of post-mortem brains we analyze in Jülich, slice by slice. But for this is really parallel computing needed, hence we have the latter part of this lecture really looking into why parallel computing is helpful in this and why we need parallel and scalable algorithms for this, right? Again, this is an example we said, be careful when you go now into practice and do the clustering. What you can assume is basically that they are not always very beautifully, out here in different spheres. They largely overlap in here and there. Some clusters may be considered as one, and this is not so easy. However, when you look on the methods, it's quite surprising. We have quite lots of them. So if you look in the literature, there are actually lots of different clustering algorithms for different parts of your problem. So you have a hierarchical kind of clustering that you kind of see here, where you try to combine information on different layers together. You have a kind of centroid-based one, where you think about k-means, you have a kind of real center that you orient towards your cluster. Again, using maybe Euclidean distance, and think all my closest point to me as a center will be one cluster. And here is an example where, for instance, I have two clusters, just putting a centroid over there. This is where we also talk a little bit about it. And then you have the density-based aspects, where I said already in the beginning, when we think about the cells, right, there is some sort of notion of density in the cell cortical regions, that they are different. So hence the cell density, or here in general in this density-based methods, that helps a lot. And finally, there are distribution-based methods that, of course, all of them share a little bit similarity in a sense, where the probability distributions help a little bit of understanding where could be potentially clusters sitting. So these are the, let's say, all the clustering approaches that are existing. We basically have no prediction when we do this. We usually want to discover something, or we want to prepare data, partition data in different clusters, not in terms of computing clusters, more in terms of data clusters. And then basically takeaway message is usually much more harder than supervised learning when you do this. In terms of the CRISP model, you would also sometimes think like I would do it as an explanatory task. So I would like just to find out more about the data set. I'm interested in classification at the end, but still I do, let's say, some analysis really with a small number of clusters to see where I can focus on my data. So maybe if I see some clusters, I will remove some of the other data which doesn't make sense and just will focus on those which are formed clusters in order to do a certain approach. So this is a really broad class where you also have to think, it goes a little bit into the domain of features and feature engineering, because you don't have supervised aspects, you also try to understand and learn more about the data. So it's really a continuous approach here together with looking at the data. A bit more concrete, what are the algorithms and methods around? And I could now spend 2-3 university lectures around each of those, which I don't do and don't have the time today. We focus on two, which is basically k-means clustering. K-means is just a kind of small, let's say, variation to it. And then DESCAN is something that we will use here in practice. Just for the sake of completeness, you should know that there's also this ZAN algorithm often used, which is more a tree-like data structure, a dendrogram, really, which has here and there for several of the approaches in clustering very good results. And then CURE is another one, basically, that is an interesting approach for different representative points. But all of these, really, to understand them in detail, we need much more time. So hence, if you're interested in clustering, don't only focus on DESCAN and k-means, for instance. Often, many books focus on k-means, which is the most simplest clustering algorithm you can get, with very bad properties in a sense for some of the data sets, right? You have to study, if you want to have clustering a bit more successful, these three here on the bottom, especially DESCAN has very nice properties, also discovering noise. So we talk about this a bit more in detail, but let us as the first example, the k-means, and for that, we need a little bit similarity measures, right? Also later for DESCAN, something who probably some people have already heard about the Euclidean distance, right? So who has heard about that? Actually, lots of many people. So the ruler distance is basically here the official formula if you want. But of course, this is an interesting similarity measure for us if you think just consider points, right? And this is an interesting aspect, so we can skip that. And here's just the k-means clustering approach. Who has used k-means before? Okay, who knows exactly how to pick k? That's a question, right? So, hence, an unsupervised problem, right? K-means is now the idea that you would have so many k's as terms of centers of your clusters, right? And you can see here people have picked the clusters somewhere here, and then now we have k3 and K4. The different colors are actually the centroids, and they are basically created by just picking them, basically these 4 Ks here, in this particular example, as, let's say, specific points here. So the mean would be then basically the error around all of these clusters and building all of these points here together as one cluster. So this is the kind of different values of K that you would use for that. And again, the ambiguity. So you think like, okay, this is pretty obvious maybe. This already is something where you could be unsure if that's really 2 clusters or if that's not really like here, the big one cluster. And here's where it already starts, this is ambiguities, right? So this trouble of picking K is just one example of that. So you have a very nice algorithm, it will have the mean error in terms of distances, and will do automatically this, but you have to pick K. You as a human have to pick K. Right? Of course there's now, let's say some helper algorithms that here and there you can try out things and automatically also help you in this, but in the end it falls down to this problem that you basically have to pick that yourself. So that is K-means. And how it works really is a very simple algorithm. You basically have to pick this number, right? That is not simple. Hence, you probably need validation, and aspects like this we will talk about later, or basically also tomorrow. And then you randomly assign a number basically to each of the observations. So in the beginning, of course, you don't know, right? So basically you say randomly you're this or that cluster, but then over time, in iterative approaches, K-means will converge to the one you picked at the centroid, basically it's the center, and then we'll be creating, after so and so one runs, and you kind of pick then after certain amounts of run what would be the best. I have also a video to show you a little bit more how it works, in a kind of moving picture. And then when you see, of course, that the cluster assignment stops changing, that's your exit strategy. So you would basically go iteratively to K-means again and again, and if at some point in time basically the cluster centroid and the clusters rounded all the assignments to the point where they'll not change. And this is your exit, you go, okay, now we have to finish this clustering. So here's an example how that works when you think about, you pick for instance K3 and then you go, step by step iteration. Step A, you just initialize these points, and as you see from just using the kind of distance measures, and then the proof actually moves more into the center regions, right, of this. You can call the point kind of gravity, the centroid of the cluster, just by basically minimizing over time now the distance to all the other points in the cluster, and here and there the dots, of course, then will change color here and there on the boundaries and so forth. But in the end, this is how basically the cluster works. And it's a very, let's say, easy approach to clustering. However, you have also a kind of, I would say, convex property. You see that somehow there must be a gravity center, but what about when I have a cluster that is somehow really much interlinked with another cluster, right? And there's a little bit, let's say, space between us. So all of this would be not really possible by moving with the centroids, right? It will be back and forth. It's perhaps not completely obvious, you will see how that materialize when you look at DESCAN, where K-means, for instance, in some situations fails. There are lots of usages still for K-means, and here's just a few of them. It's the advantage is a very simple algorithm, right, and everywhere implemented, so you will find nearly no machine learning or package from MATLAB or R, whatever tool you use, everywhere is K-means. While DESCAN is already another story, some of them don't have it. And of course this means implies that, this must be somehow a property in the data. And an example I just said, interlinked or U-shaped clusters, right? So there's absolutely not a chance of actually clustering that with typical K-means clustering. For this, of course, you need things like density-based ones, which is more the DESCAN, for instance. Still, as K-means is very simple, so to speak, using it for large image processing, like here the example I just quote, by reconstructing, for instance, all the pictures, cluster them on the geography of here, I think the Colosseum in Rome, this is something which you can use clustering very nicely. So it has very applied practical aspects of this clustering just to find out, okay, which are the parts that fit well on the geographic practice to make, for instance, here this point cloud again with real pictures, a bit more colorful. What that means will be also explained more in the point cloud dataset example. However, how it works is perhaps best explained when you think now about the video. So let's have a short video about the training clustering here. So you see here it's 5 classes. It's just randomly picked, right? And you put and initialize them everywhere. But over time you see that the centroid moves a bit, always into the center of these assigned clusters, minimizing, so to speak, the arrow in the different kind of distances. And here's another example. It uses all of this and actually moves, and again here, right, and all of these is now the measurements of the similarity or the distance here really, and then calculate the algorithm, minimize, and then go to the point and switch the position. So in a way, a very simple algorithm. I think by now you probably get the idea. And it is still the trouble of K that is bothering this algorithm, right? Really problematic. And there is not a real mathematical formula that you can use for that and say, that's how I initialize always K. However, so let's come to another algorithm that has not this problem of K, but has another, there's a question. Yes, please go ahead.
So, with regards to the initialization, you randomly assign them, the clusters. Can it be the case that after several runs you get different final clusters? Because
yes, depending on how you initialize. So the question was for the audience is that depending on how you initialize randomly, if you do that, of course, initially the kind of centroids, and then of course it would be not always causality in the end of saying it would be always the same clusters, right? So depending on the initialization, some of the points may go rather in this or that class, but it is possible. But in many cases it is clustering, because they are unsupervised, they follow a little bit the path here and there, except those which are very obvious, right? And where they maybe switch here and there between the different cluster IDs. Especially in ambiguous cases where we have seen there overlaps of traditional clusters. This would be the case that they hop between one cluster and another one probably. So in this case you probably then just stop at some point iterations and say after 1,000 runs just a couple of them hop and then you stop. Alright? Okay, any other question? Then we proceed to DESCAN. So DESCAN has an interesting other property that will help us perhaps with the problem of K, because we don't need K. This is a very nice property in the sense that we don't need to know how many clusters we want or we need basically in the end. It finds the number of kind of clusters that we require automatically, but that is very nice. However, in order to do so, we introduce different parameters. So K means that the trouble of parameter K. Now we have a trouble of parameter epsilon, which is the neighborhood, so to speak, of a point. What that means, I talk later a little bit about it. And basically the minimum number of points you assume within such a neighborhood. So you see 2 parameters, and when you use it now, basically in this lecture on the HPC machine, you will see that we play around with these 2. Like E is epsilon and the minimum number of points. And this will determine different results again. Right? Initialized differently, minimum number of points will basically do different things. So how it works, essentially with this DESCAN, it uses again similarity measures like the Euclidean distance, but now has a kind of depth-first strategy. So it's not bound to the convex problem of k-means, which means like it first identifies all of those which are, let's say, core points that has, 4 minimum number of points around them, and go through each of them and continue the process. So you would go to the next and check, is there a minimum number of points basically around me, then I am a core point, right? It depends apparently on this parameter, and of course how big is your epsilon. right? So the next step that is done when you consider maybe a border point, you will see at least one, in my epsilon neighborhood is a core point. So there's a border of the cluster, right? And you can see the mathematical foundation if you want, basically in the publication here from Esther, but that's not the key of this tutorial. We want to really use it in practice, but that is essentially how the algorithm works. It does a depth, point by point assignment, so to speak, of these different cases. And then you find some let's say, special cases where you say some of the core points are density connected, not directly, but over the course of other core points connected. So it's still the same cluster. And you see it has a form of set of rules it goes to. Not like in k-means, like having the ruler distance and then average and so on. Here you have the point that according to different rules, which are basically these density reachable, is a point density reachable, is it directly density reachable, and so on, through these rules and establishing core and border points, you basically establish different clusters, and you go by visiting all of these different points. Hence, as visiting is loaded, you need an indexing, a good, let's say, preparation of the data and sorting. One special case I should mention, which is quite interesting with this algorithm, it is able to detect noise automatically. And noise can be considered all of those which are not a border and not a core point. And hence it is a very nice algorithm by side effect, so to speak, actually finding noise in your data. And this of course depends again how you consider min points and epsilon. So this would be crucial to pick. And again, there's no mathematical function that says you have to pick epsilon 300 or minimum number of points 100. It's something you have to explore and basically do. And here and there you could do validation studies again, cross-validation, or basically grid search in a sense to find the kind of parameters explicitly. But here and there, of course, randomly makes also sense because it's a huge space to look at. And in some cases, of course, the visualization makes sense. So what we will see also in the point clouds. However, take away the message, these two parameters are important and they will pop up in your job script in the parallel job description that we will allude later. And now, a short exercise. So when we think about now how that would work with k-means, the left hand. Anyone has an idea how that would work with k-means? Would that work? Good, everybody knows, but why not? If you think about it. No, we can pick k equals 1. I think there we can win. The problem is really, again, if you see, for instance, here the U shape, right? So it would pick the centroid of those, and all of these points would be put in the gravity. Some of my students actually always consider it as a black hole. It's maybe a good idea to think about that, right? Everything surrounding will be absorbed in that cluster, which is here not the case. A human eye can do this instantly, directly right? But basically the k-means has not a chance. So DESCAN is different, but it has not this kind of centrum of gravity. It just starts basically at the point and goes step by step to each point. And we'll see, let's assume we have a minimum number of points equals, 4, as we had in the example. Go step by step around and finds these things. We'll maybe identify this, then here and there, okay, this is out of my epsilon neighborhood, right? So it's not anymore my cluster. And with this, it actually moves all the way, if you want, through interesting arbitrary shapes. And this is one of the key properties, really, of the DESCAN algorithm. And now if you can consider maybe the minimum number of points number, if you put it a bit more higher, for instance, as an example, perhaps this would be a little bit different, but you could maybe identify even this as noise, right? If you set the minimum number of points now here, let's say there would be around 20, and you would say, okay, this is really a noise in the data set, this is a real structure that I want to find. So, of course, now it's the possibility with these min points in epsilon neighborhood to play around and to look what is really the clustering about. Hence, visualization, of course, in this unsupervised learning makes a lot of sense. I should just make one remark. And there is this interesting bow tie concept, right? If everybody knows what a bow tie is, right? So these are problems where DESCAN is basically, I think, the only data structure, so to speak, a very specific setup where the DESCAN fails, right? Because basically then, in the middle of the bow tie, you lose the property of having your minimum number of points. And so your cluster gets basically diluted and thinks, okay, it's 2 clusters, while you think maybe the bow tie structure would be 1. Right? So this would be the only one where you have to think about when you use DESCAN, take care that you don't face these structures. Okay, but everybody understood why K means doesn't work here, right? That's key learning effect. Good. Hence the exercises. Maybe short, a video about DESCAN, again a bit more formalized and maybe have a more living video about this, with some applications.
Howdy. The technical problem that will be discussed in this video is clustering. Clustering is the process of grouping similar objects together. In other words, clustering can be thought of as a search for similarity. The topic of clustering is particularly important and interesting as it deals with how a rational agent would understand similarity and how it could use this concept to categorize items. One approach to this problem is to relate similarity with distance. Under this approach, 2 items in a search space are similar to each other if the distance between them is small. One algorithm that takes this approach is DESCAN, or Density-Based Spatial Clustering of Applications with Noise. The DESCAN algorithm takes 3 parameters as input: a set of points to be clustered, a neighborhood value that is used to set the cutoff distance for similarity in the data set, and a min points parameter that defines the value at which a neighborhood of points is considered dense. For the output, DESCAN will return a collection of clusters where each cluster is a high-density region in the search space. In DESCAN, a single object is represented as a numerical point in some space. The neighborhood of a point is the set of all points that are within a distance set by the neighborhood parameter. In this algorithm, each point is first labeled as either a core, border, or noise point. A core point is any point that has at least min points in its neighborhood. A border point is a non-core point that has at least 1 core in its neighborhood. A noise point is neither a core nor a border point. Noise points represent outliers in the dataset that don't belong to any particular group. Next, DESCAN assigns each core and border point to a cluster. The algorithm picks an unassigned core point in the dataset and then performs a depth-first search starting at that point. For the search, let X be the current point being explored. Now, add all the points in X's neighborhood to the same cluster as X. Then, recursively apply the search onto each unexplored core point in this neighborhood. The resulting tree structure represents a single cluster of points. The DESCAN algorithm repeats the search until all core points have been assigned to a cluster. Overall, DESCAN has several benefits. 1. This algorithm can discover any number of clusters. 2. The algorithm can find clusters of varying size and shape. 3. The algorithm can detect and ignore outliers in the data. However, there are a couple of drawbacks to the algorithm. DESCAN is sensitive to the choice of the neighborhood parameter. If the neighborhood is too small, then a sparse cluster would be labeled as noise. If the neighborhood is too large, then dense clusters would be merged together. Howdy. The technical problem that will be discussed.
No. Okay, this really concludes DESCAN. Any question for DESCAN before we move on to the applications? Going once. Twice. Okay, if that's not the case, then let's continue with the applications. Just a small feedback. Who has used DESCAN in practice, maybe, already? Okay, one, yeah. Not so many, two. Okay. So it's an interesting algorithm to study, hence we parallelized it also, because it's really effective in really practical situations. Even if you have the drawbacks and the parameter studies, but as we will see, and that also motivates a bit why we use parallel computing. With the parameters, we can cope a little bit by having lots of computing power in the clusters. So the data sets we're going to use in our practicals will be point clouds. So this is lasers. We used point clouds before. Point cloud data sets from laser scans. Okay, a couple or two. Okay. So these are basically laser scans. Could be a drone. Could be a driving vehicle. You see here one example that we're going to use in our practicals, which is the inner city of Bremen, basically. And you see a little bit where the car was driving here, right? You see a little bit of noise always here on the bottom, meaning basically literally the positions where the vehicle was and shooting the laser out, getting the positions of the building. However, in the sense, this is then all just point clouds, so kind of lots of data, not with this kind of color schemes or heat maps or whatever you use then in scientific study. You have some unstructured information. A little bit structured in terms of where the geographic position is, but the rest you have to cluster yourself, like the buildings, for instance, right? What you see here a little bit more in detail. So in a way, you have just lots of points, and what basically then the algorithm is doing is cluster all these points, all these laser scans back together to buildings, right? And this can be done, of course, in the, let's say, small data here within one city. Of course, where we are in research looking at is kind of this approach here, which is the kind of the whole Netherlands here really as a point cloud. And this is a study together with TU Delft, where we started to look at point clouds from a very, very large perspective. And if you look to US, they have actually also the point clouds of the whole different states, right? And then you can move in, zoom in, and there's actually a point cloud viewer that I just want to demonstrate why parallel computing is important and why that needs to scale, which is basically available here. But it seems like the bandwidth is not so much helping here to do that. It's, if you Google it, in2pointclouds.nl, and basically you can zoom in and zoom out in the data, but I think basically the bandwidth here is not good enough to show you that. But the point cloud viewer in this whole Netherlands example is available on the web. And of course, it's one of the applications when you think now about big data. So you want to zoom in some of the cities, you want to cluster something to understand how it has been actually the kind of city evolved perhaps over time in aspects like this. So it's a very interesting aspect and a very lively research field. So a lively research field, for many reasons, this is one. You can go within buildings. That is, for instance, a very interesting award that was coming out of Aachen. It's the Dome of Aachen. Although I just have pictures, I think, given it's so prominent, we kind of want to have a small video about this. It's very short, just to give you the illustration. What you can do is point clouds. Right, you go inside the dome and have shot lots of laser scans, so you know actually the geographic of the dome, and then you take pictures and photos and project them basically on the surface of the point cloud. And with this, you can reconstruct basically in the computer very precisely the Dome of Aachen. You can move through, fly through, an absolute realistic reconstruction basically based on this point cloud technology. And this is now something where you can, of course, then also use clustering for get some interesting properties out of the materials, out of the parts that has been constructed, out of the windows. So lots of study topics on this historic monuments, right? And this has won the Leibniz Prize, I think, as I remember correctly from one of the colleagues in Aachen, by doing all of the study related to visualization and so on, which is live covered here in the video. Just a short example of why people are so interested in point clouds, and you can go on, but I think we're interested in doing that ourselves. So now it's time to go again to your cluster, walk with me, so to speak, because we will learn a couple of things about the HDF5 format and why we cannot really see the points so much. Of course, so now it's the time to basically go in this direction, which is shown there, just a little bit to show you where the data is and actually what sizes we're talking about. So again, we move in the directory where we have the applications, we go to again, we have the tutorials, machine learning, we're still in clustering. And what we're interested in is in the Bremen dataset, right? We look at this. We see there a couple of them. Basically, if you move to there, these two are real datasets, Bremen and Bremen small. And this one, Bremen clustered, is already a little bit transformed, something I will basically talk about later. But here you find different, let's say, point clouds. One is a smaller scale, apparently, as you see in the number of gigabytes that is available in all of those. Right? So when you now use these, of course, in your, let's say, MATLAB or in your R, and here and there is a small data set probably will work, while the large data set will probably also take already some time. This is, of course, depending on the parameters you pick. Right? However, if you now do following, which is perhaps a little bit not satisfactory, if you do tail, let's say Bremen small, which essentially says give me the last bits and pieces of it, you get this. Can someone explain why? Okay.
Looking at binary data?
Absolutely, exactly. So this is a problem that you have when you basically look in the HDF5 format. And this brings us again to the machine learning pitfalls here and there, or the problem why machine learning people also have to really think about more about infrastructure, services, about tools, that really have data formats, converters, and so forth. So what we see here is a HDF5 format, and I will explain a little bit around this. Of course, normally it takes one university lecture or their whole supercomputing tutorials, 3 days, just on HDF5 and parallel I/O and NetCDF, which is another format often used. Just take away the message. Of course, this already helps a lot because it's based on a parallel file system that we can't see, right? So they use GPFS here in Ghent, and underneath that supports a concept called parallel I/O, which already now is a very much win when you think about big data sets. You don't have that in MATLAB usually, or R, right? You basically have no processors like, for instance, 20 or so that at the same time can access a file, which is a key to parallel I/O. So this is basically the data sets we use. In our job script, we will always copy that to another location, right? We will come to this in a moment. Just before we go there, of course, this is a structure where now all the points are, right? Unclustered, right? So think about there's no clustered information around these yet. And of course, how the algorithm now works is they should go through all of these points in the HDF5 file and assign clusters actually to this kind of, different point cloud inside these files. So it reads, the algorithms read it from HDF5, but they also write it in HDF5. Hence, all is binary, we can't see it, and we need a visualization for it. And the visualization is a point cloud viewer that is available also to you and is installed. But for that, we need to transform of the format to a point cloud file, which is here. So this is not anymore HDF5, and I will demonstrate this later. But for you, I also put the converter here in the scripts. So if you want to work with this, after the tutorial, what I encourage, right? This is something where you should think about when you want to displace this in the point cloud viewer. You first have to go through this converter of saying, once my Bremen file is unclustered, I cluster it with my algorithm. Then basically once it is clustered, it contains the information of the cluster. But in order to visualize it in this interesting point cloud viewer, I have to use this Python script, actually putting the HDF5 file to the point cloud viewer format. Right? And with this, you then can visualize it. I will do a demo later. Just that you have basically all the tools to do it yourself after this tutorial. Because we are very time limited, we cannot do, let's say, very much things because we also want to move to more sophisticated models. But of course, this will remain available on the cluster, and you can use that at any time. So this is the the kind of aspects for Bremen. If someone wants, after the tutorial, be clustering a little bit around Twitter tweets, we also put the data here on, having some Twitter aspects clustered. We cannot cover that because we don't have really time today to do that all. But this concludes a little bit the idea around the Bremen and the point clouds. Maybe another just short video around, another site which was also a laser scan. You see, especially in history, it is completely different what you can do there. You can go through buildings which you otherwise could not really explore very much because they're kind of historic buildings, especially protected. You can do certain studies, you can change cluster sizes, and you can really play with this aspect. And then, of course, this gives huge insights into times that have been, in the past, as this, for instance, example. So, and there are lots of ruins from the Rome area where people do lots of clustering. There are people doing this in engineering plants to find out their pipe structures and reconstruct the pipe structures, for instance, in oil and gas. So there are lots of application areas for point clouds. Any question towards point clouds, particularly, before we move on to the parallel world, exciting and more practical? Going once? Twice? Okay, no question? Then let's have a look on parallel computing. And this is a space I have whole lecture series about it, so I will keep it very brief. Who has used HPC machines before? A cluster, job scripts, knows roughly about all this. Okay? The others, don't worry. As I said, we have here experts which help you now establishing the job scripts and copy these to your files, to your home directory and so forth. Just a little bit of a start. HPC, maybe some of you have heard about Hadoop and so on. HPC is really where the cores are very much interconnected. That means we have a very good network interconnect between the different kind of cores, which gives the algorithms good performance, for instance, for HPDESCAN or the parallel version of DESCAN. You think about there should be density connected. Even if you're large clusters, lots of communication must take place to understand, informing the cluster. There are also lots of Hadoop implementation, but they generally lack the good network interconnectivity, right? We call that high throughput computing. Yet many data sciences are using HPC systems, right? But the power of HPC should be not underestimated when you do basically the kind of machine learning algorithms. The system we are going to use is basically the golett cluster. You have already used it a little bit using your SSH key, so let's continue. It's now important when you run your jobs, because we have a specific reservation that you use this one, golett. So when you log in, you can see all the files, because all the files are always the same on all the clusters, and it's actually the same when you go to Leuven or so. But the key point is now one command I will show you in order to use this golett cluster. The details of the cluster basically is best explained by these categories. So InfiniBand, this stands largely for a very good interconnection between the different cores. We have powerful CPUs, and we have a 12-core Intel with 2 times 12 cores, so 24 actually in a sense here on the node. And then the memory per node is 64 gigabytes. So this is something which of course affects now our speed up, our work the next 2 days or today and tomorrow. So how you do this? When you log in, right? You log in with your typical credential, SSH, as we have shown before. You will already get basically this message of saying, okay, these are all the clusters and how many running jobs and so on. And for us, particularly golett is important. So whenever you do now your jobs and log in, and after each of the login, do first the module swap cluster golett command. Okay, so this is something what you should do now. Log in to the cluster with SSH and do this particular module swap cluster golett, because that is important for us when it comes to the switching the right cluster and doing the practicals. So I exit here just to demonstrate it once again. And for those that are not so Unix inclined, the arrow up usually means you can look in the history and see what you have done before. So module swap cluster. It's not golett, it's golett, right? Right, so, and then actually it stands for a Pokemon, as I learned, right? So I think I have to go again and look a little bit more at the Pokemons to really be familiar with all the names. And but it's a very nice idea, and usually you find this. In Jülich, we always have the U for everything. So we start Eureka, Julia, Europa, or all our systems stand for U. Everything must start with U. So we don't have the Pokemons, unfortunately. And sometimes it's a difficult finding a name if everything has to start with U. But anyway, having done this, basically nothing changes. When you now look in your home directory, that's still the same. You can still access, the applications and the clustering data and everything that we have learned before. So what's next? By having done this and swapped now, we basically now use the HPDESCAN algorithm. I don't want to really introduce that very long because we want to do some practicals around this, and there's a nice paper. Just take away the message, there are several ways of parallelizing this, but if you look in the Spark, Hadoop and Python domain, you largely find no really parallelization schemes of DESCAN. So if you want to have big data as clustered, you have basically literally just two implementations, one from Northwestern here in the US and one European approach, so to speak, and they are based on MPI, which is a message passing interface, lots of communication between the different CPUs. And it's actually a hybrid, it uses also shared memory. Things that all of you don't necessarily need to know, technical details, but if you're interested, we have there a paper studying the differences, and actually we are much better in scaling than this one, right? That's why we created also this here, but for the details I would refer to the papers. Just a few side aspects, how it is parallelized, think about it. Now we basically have again the cluster that we already know before, that we have used in one of our exercises on our own. But now, of course, we want to parallelize this, which means we lay a hypergrid over this space of all the points. However, this means you first need to know the space, right? So you have to get all the point clouds, in a sense, here for simplicity, just 2D, and basically then do an index around them. So where are they? So this is something which is a first pass through the data. You have to index, sort, and then you can enforce, of course, HPDESCAN. If you remember, these two really count, epsilon neighborhood and the minimum number of points. And these are the parameters you use also with the HPDESCAN. And from this you derive then the optimizations. Just a little bit one side remark before we go to the practicals. Of course, one typical question is, how do we know how the data is actually structured? And this is an effect called load imbalance that you see here. You see here one domain by one processor has a hell of a lot of things to do, very much, different points, while on the other hand, the processor here on the right-hand side has almost nothing to do. This is what we try to avoid in HPC, and this is also done in this code. We have a cost heuristic estimating basically how much computing time there will be, and with this we change basically the distribution, as you see here, with this very more or less funny kind of cut between the data, because you would assume that is a cluster, but still it is more cost efficient in terms of CPU time of cutting here and then merge later. This merging is done with Halo regions. Someone has heard about Halo regions before? Now we go really in MPI technical details, I thought so. So take away the message, lots of beautiful MPI code under the hood, but this code is open source, you can use it in your lab every day, and just let us know if you need help with this. Maybe a few parts about what is this parallel I/O, because we're in the data lecture. Think about that, be thinking about that many processors now have to look at the data, right? So this is a parallel I/O thing, so they all need to write and load the data from one big file, as we have seen, the HDF5 file. And we do this in parallel. That means everybody has a certain I/O amount, and instead of having all their local files, it could be, right, that we now distribute the data, give them all the data. We basically here have one big file that we use and go the write and read. And this is something which is in MPI beautifully supported with MPI parallel I/O. Maybe from the structured file, we have seen the parallel file system GPFS, which is largely standardized in POSIX I/O. MPIO is here basically in between as a kind of middleware. And then you have HDF5, like the Bremen data, but also NetCDF, which is another parallel file format for more vector data, right? HDF is more rather a file system on its own. And just for your understanding what a little bit the technique behind. And you use it really transparently in your application. You have some libraries that help you. So the HDF5 is an example of such a library using internally the I/O, so that you don't really see that. Right? Basically, it's inside your MPI code. You don't need to worry about it. All you would need to worry about is that HDF5 is a file that you require for the clustering. Now, how HDF is basically looking like, you can consider it here as having some beautiful arrangements of some more complex data structures. Instead of just having an integer or basically just here in float, you can construct things like here, where you have a different, kind of array always combined with different, types of, floats and integers. As an example, forming a record, and then you can put the record somewhere in your HDF5. And hierarchical stands for the fact that you basically have, like a file system here, the kind of hierarchical approach of storing data. And this is the standard format. Wherever you go in science and engineering, people will understand the HDF5 format, and many of the tools support this format and NetCDF as well. So much for the theory. Everybody has, now an understanding about HDF5. Now for the practice, we cannot just use it like MATLAB now and R. And usually many of my machine learning students are not familiar with this environment. Here we have like 40%, 30% have already used the cluster. You basically ending up one like this. This is just a kind of system in Jülich, just explaining why scheduling is needed, right? All of you are using now this golett cluster in parallel. That means you get scheduled somewhere here on the machine, right? In order that this is not affecting someone else, what you do, there's a scheduler in place, which in our case it requires a job script. Now we have to talk then, therefore, how you do a job script and copy that and use it. So this is the first part, and this is available to you in the part here. So the first step would be again looking on your part of the data directory in the apps and tutorials, machine learning, clustering. Where is it in scripts? No. Did we copy it?
You have to copy it.
Yeah, but we didn't copy it yet. Okay. Sorry for that. I don't remember. So I will copy my script here. So everybody from you now should basically do the following command. You have now this kind of job script that we require in order to use this machinery inside this particular directory. And in order to just copy that, you can do the following of saying, for instance, there are different ways. Those of you who are familiar with Unix, just go ahead, copy the file to your home directory. So those of you that need a little bit help with this, you could do, for instance, this, and say, you just make the absolute path here. And here it's important that your big, and small letters always match really the thing that you have. And basically put it, either if you are in your home directory, you can do just a point, but you can also do the tilde here, and this will automatically translate and copy then this basically to your home directory. Right? When you've done this, you should have in your home directory not so much that I have here right now, because you see I already did, of course, some runs to test all of that, what we will do now in practice. But you will have in your home directory this particular one, HPDESCAN _example.sh. Right? So when you do ls-l in your home directory, there should be now this HPDESCAN example.sh. So who of you has done that? Okay. Those of you who have not done it, why not? And please talk to the gentlemen. Raise your hands, right? You get help from the people. We have a couple of people helping now. Where are the problems, copy problems? And just for the sake of us as a team, we wait 1 minute now that these guys can also copy the data inside these different aspects. Again, the file is located in this particular directory. And inside this you find the HPDESCAN _example.sh. It's a job script we will describe, we will look at together, we will change it together, we will have it say let's use together with the machinery here in Ghent in order to cluster the point clouds. But this is really the first step. Please copy that to your local home directory that you identify with tilde. If you're in doubt, do cd change directory tilde and you basically find in your home directory. Again, if you have troubles or problems in copying, just raise your hand. There's another one on the back that could help you, and so on. So again, the copying command would be then that you just use a CP for copy. You would have the complete path to this script. So not only the directory, also the script itself, to the position of tilde copy. And that should work so that you have your own instance basically in your job directory. This is needed because now everybody of you will modify it, everybody of you will create a job out of it to the cluster and compute something on the cluster. Okay, anyone still has problems? Would like to have help? I think clear in front and there. Yeah.
For the people who want to submit the job script already, keep in mind there is a reservation. You should have gotten a mail this morning that explains you how to submit a script into the reservation. So make sure you do that. Anyone else? Everybody have the job script?
Okay. If you don't have the job script, scream now. Going once, twice. Okay, let's go ahead. I think the first modification you should do is actually what Kenneth just said. So perhaps Kenneth, I can get you to the audience here and edit this in the job script, which means the reservation, right?
I told them in the mail to just do it on the command line.
Yeah, oh, okay. Or we write it maybe on the smartboard, but the smartboard should not be on.
They got it in the mail. So everybody should have gotten a mail that explains you how to submit in a job script. Now I have to think myself. Don't know it by heart, but if somebody sees me making a mistake,
I think you first have to type flex double point and then ADDRES.
No, the X was right. X equals then flex in.
You get the letters.
and this, and then the name of the reservation, which
Machine
is
learning point 316.
Flex should also be in capital letters.
Okay.
So this is something that unfortunately after the tutorial will not remain, right, the reservation. So this is something just now so that everybody of us can directly get access to the cluster, where we should be also thankful about, because now production users that use this cluster for their science and engineering problems actually will not be able to use it. So thank you very much, Kenneth, for arranging this reservation. But just take in mind, when you leave this tutorial, you are just encouraged to use all the material, all the data will be there, the job scripts will be there, you can use the cluster, but the reservation will be gone. So you can use the reservation afterwards.
This is also why we don't put the reservation in the job script, because next time it will not be there if you don't change the job script.
Exactly. Right. Just take that in mind. It's now like a special setup just for this tutorial. Right. So having done this, you now see, okay, we have the job script, and now we submit it. What is actually inside the job script, right? So let's look a little bit more into the job script, into the practice, how that is used, and how it maybe reflects here and there a little bit what we have just learned in the slides, right? This is interesting. Maybe for those of you with the editor Nano or VI, Emacs, I mean, whatever editor you like to use, please go ahead and use it. I use here the VI, but you don't need to do that. In some ways, it's a little bit complicated to go through. However, I just want to spend a little bit of time while others still copying and so on to explain a little bit what this job file is about. And we see some analogy to the slides we're talking about. Right. First of all, these are always cluster scheduler commands. Right. This is kind of interesting comments here in PBS. It's a type of cluster where you specify the wall time. That is something where when you hit this wall time, your job will stop automatically. We talk about it will run against the wall. Right. This is a kind of maximum time you use for this job. It should be relatively as you assume, but really not shorter than this, because when it computes and it hits the wall time, then it would be just stopped, your job, right? So do it, let's say, a bit more than you would expect, put some buffer, but please don't use 4 hours for a job that is 10 minutes, right? The reason is because a cluster assumes and will actually work with this time to schedule it on the machine. And with this, of course, you would have then problems in scheduling when you say you have a 4 hours job, while you can maybe be backfilled if you have just a 10 minutes job, and will be, you know, there will be some place in the scheduling for you just for 10 minutes or so. So it relates a little bit to scheduling and lots of theoretical details I want not to allude to. This is a very important command as well. So this actually indicates how many, you know, processors per node, so how many you would use. For instance, we have learned 2 times 12 cores, if you remember, so 24, all in general for golem or golett. Then this is what here this indicator all stands for in one node. You're basically free to change that, but do that in mind of being friendly to your neighbors. Right? When you now do nodes 100, you will get in some trouble that, you know, others also are not scheduled. When you do, let's say, a couple of more, that is not a problem here. However, I would like also to talk a little bit about these aspects. A module load just means whenever you want to use HPDESCAN in the future here in Ghent, in Leuven, in different, you know, computing centers, make sure HPDESCAN has loaded this module. And also this my MPI run is a specific MPI environment that is existing here that we'll use later. Right? So this should be always in the job script, just preparing the environment and the executable for you. Because otherwise, when you now execute it here in this example with this command DESCAN, it will be unknown. Right? Because it will be not there. It is just coming out of the HPDESCAN environment that was already created for you. The executable is there. However, it's just the executable, so we have to talk about data. Right? So where do we get the data from? So the second aspect is here, we create a working directory, which is a typical way of saying a sandbox is created. So your job will run not usually in your typical, let's say, home directory. You will be scheduled, if you remember, somewhere on the cluster with 12 cores, 24, 6, no matter what you kind of pick. And there you create a kind of sandbox working directory where your job will run. That means the results will be put in the sandbox.
and we have to put the data in the sandbox to be computed. Right? While the whole cluster knows about the executable, the DESCAN now, because we loaded this module, and so on, the job script will know, we still have to think about the data. So that is what we do here. We copy this particular one, the Bremen small, in this example, but you're free to experiment also later on. That is one idea of the exercise now, of put Bremen small and also the big Bremen, and you will see the different runtimes. Right? So put, please, this always here inside, because then it's easier to basically link to this kind of data. And this is particularly important because of what, when you think about HDF5? Anyone has an idea? When I said about we identify the cluster IDs and we store also the cluster ID in the HDF5, right? So the cluster ID would be then stored. That's why you need your personal copy about this, because you not only read all point cloud, this is of course unassigned when you actually copy it from there. They have no cluster IDs, but once the DESCAN is run, it will write inside this HDF5 the cluster IDs 1, 2, 3, 200, however it finds, and -1 for noise and so forth. Right? That's why it's important that you have a dedicated copy for each job. Why for each job? Any idea? Why we do always a copying for each job? No? And any job can be different, right? We have different parameters. That's what we have to talk now. When we think about what we discussed a little bit in the theory, we told, okay, the epsilon neighborhood is something which is important to us. So how we consider the epsilon neighborhood? This is this parameter. And also we discussed a number of points. So this is a technical parameter that you can avoid in a moment, but this is like more to the implementation. But these two, you remember from the kind of theoretical parts that we had around DESCAN and the movie or the kind of small video, right? So depending on how you choose the parameters, of course what you write then in the HDF5 will be different, right? So depending, if you have a very, very, very small epsilon neighborhood, of course this could be a totally different outcome than having a very, very large epsilon neighborhood. And if you remember a little bit about the video, this means basically sometimes eating whole other clusters because they're inside each other, for instance. So all of this is now depending on how you switch and work on the parameters. However, what you should explore a little bit now is play a little bit with the epsilon parameter and see how it also changes runtime, right? So we see that basically over time you will submit the job with QSub, we will come to that in a moment, and you will have different outcomes. And this basically you can see then with Point Cloud Library Viewer, which we cannot do in the tutorial because of time, but please explore now, basically while I'm talking, and also throughout the lecture 3 that will come, right? Play a bit with these parameters, and whenever you have a problem, also raise your hand, that you know a job is erroring or so. Usually that should not happen, but could be if you pick, for instance, a parameter wrongly, or you avoid, let's say, -e. This DESCAN really needs this parameter E and M, so if that's not there, there are errors. We help you here in submitting this. The reason is it will take some time to cluster, and I cannot just wait here every time a run is happening, right? But we will come back, and that's the idea after lecture 3, for a discussion round around. So what you see, I will do some demo of the visualizations of the different clusters and so forth. So, and as you basically see here, that's a very nice quote. The work directory will really help you to find again your HDF5 for the specific job, right? Because every time you have a job, you have a new sandbox created. However, the sandbox will disappear also. Is there some policy actually, Kenneth, when you normally remove it?
We don't clean up scratch. No.
Okay, no, in the moment, so it will remain here and there in other centers. It will be from time to time removed after months, not used, and so on and so forth. Right, so much for the job script. Any questions maybe for the job script before we go ahead? So the idea is roughly clear. Yeah, please go ahead.
How long does it take for the first job script to finish?
The job, I think it was 10 minutes.
It also depends how many resources you give it. So if you're just submitting as it is there, it will get 24 cores. which is quite a lot. So I think it takes a couple of minutes.
Yeah.
If you give it more cores, it may go faster, but yeah. It really depends on what it's getting.
So there's of course no exact runtime usually you can say for that. That largely depends on what Kenneth was saying, how much you put in here. So if you just use that here, the nodes 1 or nodes 2, or if you specify here, let's say 12 or 24 or all, maybe the hybrid again was that we have now 6 MPI tasks running, right? So you can also remove this, right? Then it will still work and use all of them. So you can now play with this a little bit in between and use the time basically to just submit different runs, right? And the runtime of this is not really clear because also if you play with these parameters, it could be more complex to compute, right? When you have, let's say, more clusters generated, it could be ending up half an hour. Or if you have, let's say, more and more cores added here through more nodes, it will be just faster because of a better parallelization strategy. That's why you should basically perhaps start with one example, increase the number of nodes stepwise, and then explore that the job will be getting quicker and quicker done by keeping everything else the same. Then Bremen small will be pretty boring because it's a small data set. The next step might be that you now change to the real big Bremen data set. Right? If you remember in our kind of examples, we have always the other one too, and you can just exchange basically this Bremen. I can exchange this with the other here. This you just exchange the Bremen small with Bremen from page F, right? And then you have the, as you see here from the size, a much more interesting problem. Hence, back to your question, much more runtime needed, right? Because you see here, there's lots more data inside this point cloud than in the small one. But I hope it answers your question. There's really not a dedicated time you can think about. But coming back to you shortly, how you can work with that. So before this was just a job script. How you work with it is basically you queue sub it, right? That is something you have already seen. Make sure you use the reservation that Kenneth just was pointing out. So let's go to the practice again. Repeating. When you submit, do this specific reservation. Everybody of you has this in an email, so you don't need necessarily look at me. But whenever you submit your job, put these flags that ensures that you're directly scheduled, basically when you're now on the system. One way of checking where your job is, for instance, qstat -a, and it should show you if your job is finished or not. Right? And in this example, when I submit, it is already finished. So we see here the job ID, which is very important for your job outcome. Right? So this is something you should always remember, in the sense that when you here do the qsub with the reservation, you get a specific job ID back. And this number will be unique for every one of you. It is a job ID, and this is basically then the key of understanding what happened to your job. And what will happen is, when it's finished, like now, we see in qstat -a, there's no job anymore. Apparently my job has finished. I will see in my home directory here that I have an outcome of this job with the same ID, right? When you remember here now, what was the idea? It was like 1174236. 236, and there should be an outcome about 236 somewhere, which is this one probably. It's also 2 o'clock, it's relatively fit. Oh, that's an error, sorry, that's the other one. 236 is here, there's the outcome at 2 o'clock, and it has some information inside. So let's look what the outcome is. So we use this output of the job to check a few things, what happened actually during clustering. You see, it's a batch system, so you give away the job, it does magic, clustering and everything, and now bring you back the results, as written in the HDF5, the results. However, in HPDESCAN we put a few points here for showing you, what's happening. So when you think about the dimensions a bit, what took time actually in clustering. And you see the local scan took here most time, which means scanning and creating DESCAN clusterings locally. So going through all the points in depth first search and getting core points within a cell, so to speak, of the parallel domain. So once we have these local clusters, which are not necessarily the real clusters, because you cross maybe in a parallel domain to the other one, you get them connected, and then basically adjust the labels and merging the neighbors with harder regions and so on. But all of this takes not so much time. Here the most computing time is really in this clustering itself, in the local space, and then you do it on the global level of exchanging the neighbors and check if they are part of this cluster as well. And you see here the results, and this is most importantly now for your exercises, right? When you now play around, you should actually use the job script many times. QSub, 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 that's where the cluster is for. And you change the parameters from epsilon from 300 maybe to 100. Or you change epsilon to 1000. And you will see that significantly these clusters here will vary depending on what you do. And you can see here that there are noise points, so many core points, if you remember, that satisfy the minimum property, right? The minimum points property. These are found as well. And how many cluster points in general are there, how many noise points, and so forth. However, this is just, let's say, time and actually some meta information was happening to your cluster. The real data, the assignment to all of the different clusters is in your scratch space, as we said. You copied it basically in this, if you remember, in this directory by doing this line in the job script. So let's move there and see other results. So when we move there, we are now in our specific sandbox, so to speak, that we created just for this job. Very unique, has this identifier 236 as we discussed, and inside is now the sandbox. And if you see now, the data file is suddenly not anymore the size that it was before. That is because we added basically lots of new information for each of the point cloud data set sample. Right? For each of the points, it has now an additional value saying, I am cluster 3, I am cluster 300, I am cluster 5000, and so forth. And of course, noise is also indicated with a particular indicator. And all of these are then written back in this kind of HDF5 file. And with this, changes dramatically depending on your epsilon and minimum number of points. Right? And this is now an algorithm you can use for small examples that you should not have much nodes. Or even if you have more tough examples, we can also probably give you access to the whole Netherlands point clouds with some collaborations. So these are then things where you really need the parallel computing. Bremen small is still, let's say, a very digestible problem. So if you want to specify then with more cores here, some users maybe more advanced already use the cluster. When you want to use more nodes, then please use the Bremen dataset, not Bremen small. Right? Then Bremen becomes much more eminent what we're talking about. For you at home, because we also have to slowly stop this session before we continue with the other and have a small break again. All of this is kind of documented in the slides. The slides will be available to you so that you know already after this tutorial how to work with this material. Right? And then if you're interested to look what it is really is clustered Bremen, right? So now we're talking about very much kind of numbers and so on and cluster IDs. In a way you want a visual explanation. There's also a point cloud viewer installed for you on the cluster. For that, you have to do the following. Firstly, you have to do the SSH-X, which stands for X11 forwarding, so that your display is forwarded. Right? When you log in from a remote distance and so on, it's basically something you require to forward your GUIs and the viewer. And when you log in, you need this particular library that was installed by the team here. Always before you use it perhaps in some practical setting. So once you do that, you just basically have available this PCL viewer, Bremen clustered point cloud data. If you remember now, the data that you have in your job scratch is HDF5 still, right? So hence, before you basically do that, we need to do the following. We had, if you remember a little bit, in this X directory, also the converting script, right, that we require. So that's what we want to start here. So we have basically Python, and we would do the X. It's a Gent tutorial, machine learning, clustering scripts, and there was this H5 to point cloud data. Now we have to specify, of course, which file, but this is easy because now we have the HDF5 basically in this same directory here, right? That's what we just have seen here. Bremen small is not the one that is unclustered, it's now the one that is clustered, right? So this is something what you then use and convert basically to the different part. Did I need to use modulo item probably, right?
Module HPDESCAN. Yeah.
Sorry, that is what I forgot. Module load.
Yeah, let's see what we have listed. So to run the script, you need H5Pi, sorry.
I have this as well. Yeah.
If you check which modules are available, there's a whole bunch of them. It's probably a Python 2 script, so you want to use a Python 2 version of H5Pi. You load this one. And if you then try to run it, it should work. Almost. So do this on either do this on a worker node or use the software from Delcati if you're on the login nodes. So if you get an error like this, it's because you're trying to run software that was built for golett on the login nodes. That doesn't work. You can just swap back to Delcati and running interactively. It should reload all the modules for you, and then you can run this. And I'm getting the same. You know what this is about?
Mm-hmm. I think what we will do is we make this information available after the tutorial, because everyone cannot use it anyway here because our bandwidth will be not sufficient in the wireless, right? So because it's GUI, it's very intensive. So what I will do, I will make a demo what is existing before, but the script is there, and we will do a small, let's say, slide set by doing this step size. I have it here in the slides, but only, let's say, to a very rough, let's say, description. And of course, you need first to module load also the Python and aspects. I think this one is better. Can also, I didn't load before the module load point cloud, right? That is probably also one of the problems here.
No, you don't need that for the script.
Ah, okay.
It's just for visualizing.
Yeah, sure, right, exactly. So let's go there. So in order to do that, we want to first actually use this point cloud library in order to get access to the viewer, which I just now demonstrate shortly, but you can do that also after this tutorial. And then it maybe makes also sense to play around a little bit with the different visualizations that you got from different clusterings on this data. That should be it.
Do a module purge first. Yeah. Now.
Right, and before you, of course, if you do this, you should also consider then, of course, you have done this transfer from HDF5 to the point cloud. So we use now one that we created before so that you can get also a feeling about that. And it's available to you in this directory here, from clustering and then Bremen. There you find already one clustered solution which is converted. Right? And we just use this now as an example, like I have here on the slides, just to illustrate the point cloud viewer. But again, doing this on wireless with a GUI like this and with lots of points is of course something which is a little bit problematic. So at home, when you have a wired connection or let's say more bandwidth, this makes much more sense. However, while this is loading and so on, maybe any questions so far to the point cloud, to the HPDESCAN approach we have right now, the job script, the QSUB, the parameters. Any question? Very shy audience today, so no questions? Yeah, go ahead, please.
Okay, you really want one? I was just wondering, this algorithm, how does it scale with the number of points? Is it n squared or is it n log n? Or?
Yeah, because we basically have a trick, and you see more details in the paper. It's a very nice question, so the question is about scalability. And when you look a little bit, like I mentioned, we have this kind of first hop over the data where we do some indexing property with the hash map. And with this we have a beautiful, not n square property, but a logarithmic property in the data. And it scales basically the way, in the sense, adding more parameters and adding more processors, that we basically then have, of course, the different regions where we cut. We call them Harlow regions. Then where you basically have some, let's say, that are endowed, in which cluster layers. We have then in the merging step, then always to check if it is really belonging to the same cluster. That is what we saw in the runtime, if you remember, of the output. This takes a long time to do locally, and the use shared memory still is fast compared to MATLAB and others. But then here is really then the next step. Once you have done the local process, you check, are there kind of these situations here? So, when we scale up to many points and many processors, that we add them more and more, which we need to add because otherwise we have a long runtime, we add up with this situation that, of course, this is one cluster, right? So you end up cutting a cluster here, but we have a merge step basically after the local clustering is done in order to get basically the clusters together again. And with this, you scale basically limitless, I would say. However, we don't tested it yet for, let's say, extremely huge point clouds. But if you have one available, surprise us. We are also open-minded to test this, but you have good data to actually think about the limits here. As you see a little bit, maybe for instance, scaling that was asked, it's almost linear scaling in the beginning, and then of course it drops off here and there of data points. Also with a number of cores, for some of you that are familiar with simulation sciences, also numerical laws, physics, weather forecast, and these models, they are usually using in the hundreds, thousands domain more processors. But of course, think about the aspects we said now. This is one run, right? And of course, we experiment with the parameters here with epsilon neighborhood, and the hypergrid we have, for instance, is according to the epsilon neighborhood to actually have some local clustering easier. And this, of course, changes a lot. And so we have many smaller jobs compared to the simulation sciences that have one big, bold, 500,000 cores job in parallel, right? And this will be more obvious tomorrow when we do support vector machines with grid search, where everybody of you will have different parameters to look at, and then combine this information to get a model selection in the validation step. But this is stuff we do tomorrow. Was a very good question, right? Any other question, perhaps? Okay, if that's not the case, let's see if the point cloud viewer works a bit. Otherwise, we come maybe directly to it later. Okay. Oops, it's actually my fault. You see, that's why you need to use -x. You just have seen I cannot open an external connection because basically I didn't specify it by login. So when you use the kind of machinery with the point cloud viewer, you do SSH-x. There's also VNC as another approach of accessing the cluster that's probably better preferred if you want. But now, of course, when you once logged in and logged out, take away, remember that we first also have to load this point cloud library again. And of course now we also have to go to the directory, or we can this way, say in front, apps, Gent, tutorial, machine learning, Clustering. Bremen. Okay, so that should work better. Anyway, so when I now break for the small break that we will have, I'm there more for questions here, but also think now about that this tutorial is really a hands-on one, so you can, while I'm talking in lecture 3 about classification already, things we do tomorrow, a bit about the theory, always now and then go back to your cluster, do few steps, think about what is actually happening to my job, change parameters, go a little bit into the feeling of speed up. Perhaps use the big Bremen one, and then increase your number of nodes, so saying 1, 2, and if you have problems with it, here and there, Kenneth and they will help you actually in getting errors resolved, but usually it works very nice, you just have to increase the number of nodes. Of course, when you have lots of nodes and have then Bremen small, that's not really a speed up that you cannot win, right? It's a specifically prepared data set for that. You see a little bit, perhaps from the point cloud viewer now, some image, but we also explore or see that it's very slow. But if you log in and use this, you basically can scroll with your mouse into it, right? And of course you can do the same thing, perhaps when you're at home, use the unstructured one, the unclustered one, and visualize, right? Then you see not this kind of beautiful colors and clusters and created things, you just see points, right? And here you see, basically with a visual eye, a little bit problem with the bandwidth, but you see that actually the city was quite well reproduced in terms of, colors, building, and you can move around it a bit. Again, of course, it's a point cloud, so it's not a beautiful picture like you have seen in the dome. But of course, now this is the kind of starting point. Now you use photos, and visualization experts can actually bring that together to really create the videos that we have seen. Good, and here you see a little bit, I think really bandwidth makes it a bit less interactive as usual. But here inside you can, for instance, see the noise that we discussed here. Right, that there are dots on the ground, which means that is where the car was parked, shooting lasers, for instance. And you see here smaller structures, whole building parts of the front and so on. Of course, here and there, it's the same views you have here on one of my slides that I showed you earlier, which have been a little bit prepared. And now you can have different aspects of it. Also think about that scientists are using it in a multidimensional way, perhaps. It's not just X, Y, Z, which counts here. The coordinate could be also heat emission. It could be, if you think about the whole Netherlands, with people thinking about what type of area is it, and so on. So you would have studied different things, right? And this, for instance, here would be a heat map, where you see, for instance, okay, there is a little bit heat here always on the top of the things that you can analyze really if there's some here and there's some, kind of rooftops that should be probably renewed because they are, according to the new standards of the EU, preserving energy and stuff like this. So lots of application fields just around point cloud, but I need to stop now because we also need to proceed to lecture 3. And please play around with the dataset. This video we have already shown. However, I have just one video that I would like to use now in the break. Just run it for those of you who are not so much into HPC. My students like this very much normally because it has a very nice overview about what actually HPC is about, the I/O nodes we discussed, power level, and so on. But consider yourself now being part of the break, and if you're interested, just listen a bit to this video here. It's a bit longer, hence we should also now use basically the kind of break here, getting refreshments, and so on.
Simplifying high-performance computing architectures, an engineering perspective by Patricia Florisi.